Very good morning. Today, we will start with a very interesting topic called theory of automata. Now, if you recollect what we saw last class, we did see that what is an automaton. We did see what do you mean by an automaton. You saw that it is a finite representation where you will be giving in an input, you will be having in a language. Okay, you will be giving in the input and the language to a final automata, and the final automata, it will tell you, the finite automata, it will tell you whether you can reject the language, reject the string, or accept the string. So finite automata, in other words, it is a very simple machine, or you can say it is the abstract model of a digital computer. The only job of a finite automata is pattern recognition. The pattern you given as your input, you given a pattern, let's say you given a pattern called A, B, B, A. Okay, you given a pattern, you even have a language. The only thing what the automaton does is it tells you whether you are to reject it or whether you are to accept it. Now let's see, how does a finite automata work? Now this is an example which we saw last day. Okay, you have a set of alphabets called A and B, sigma is equal to AB, and then my language is nothing but the set of all strings starting with A. You don't have a D over here. Okay, so all the strings starting with A is my language. So I have A, B, etc., etc. Now you've got to check whether this particular string is valid and even whether the second string is valid. We did see how to manually check it. You take each string and then you check it with the first one, the second one, third one, and you go on, and then you check it. But this checking is actually exhaustive because this is an infinite language. It is an infinite language. And, checking would be a bit difficult. So what we do is we design an automata which can perform this task. We will try building up an automata which can perform this task of you given whichever string, this automata should be able to tell whether the string is acceptable or not. Now let's see, how does a final automata work? Now this final automata, the working is done with the help of a state transition diagram. It is done with the help of a state transition diagram. Now, how we draw a diagram, you need not worry, we will learn it later. So as of now, I just have a simple diagram which can check this particular language. Now, each language will have a different automaton. Okay, so for this particular language, I have designed this automaton. So this whole thing, I call this to be my automaton. And then I am giving in an input string. What is my input string I'm giving in? I am giving in my input string A, B, B, A. And this particular automaton, it is working on my particular language, which can accept all the strings. Now, with the help of this automaton, I should be telling whether I can be rejecting something or whether I can accept. So if you look into your initial figure of the automaton, this is the only thing it does. You have an automaton, which I've drawn over here in the middle. I given an input string, I given a language, I should be able to tell whether this automaton accepts it or rejects it. Now let's see, how does the working happen in an automaton? Now, before we learn about how the working happens, is you have to learn about two terms called state. Okay, so first we learn about something called state. Now, states can be of three types. You can have three types of states in an automaton. Now look here, I do have a state over here called A. And then A has an incoming arrow from nowhere. Okay, but if you think about B, B has an incoming arrow from A. C, when you talk about C, C has an incoming arrow from A. So, A has an incoming arrow from nowhere. Such a state, you call it to be the initial state. That is why you're going to start your automated, where you are going to start your inputting. So you have a state called an initial state. And you even have a state called final state. Okay, final states, they are always represented by double circles. So over here, I call B as a final state. Okay, so B is my final state over here. So you have an initial state and then you have a final state. And now imagine you had some things in between. You call it intermediate states. You call them intermediate state. And you even have another kind of state called trap state. Okay, T-R-A-P, which we will see later. Trap, dead, hang, those are different ways in which you call trap state. They are denoted by the letter phi. Okay, so these are the various states you have. You have initial state, you have final state, you have intermediary state, and then you have a trap state. Now let's see how we work on this automaton. Okay. So now we'll see how this particular automaton works. Now this is my question. I do have a state transition diagram and I have to check whether the string called ABBA is valid or not. Okay. Now, as I told you, all the things in circles, okay, my A, B, and C, I call them to be states. So you're very clear about what do you mean by a state. Now, you do have these edges connecting these states. And I've written over here A, B, and so on. Now, this is, you call it the input. You call these input. So, from A to B, A is the input state. B is the input over here. Here, AB, and then here also I do have inputs AB. It means very simple. From state A, when I encounter an input called small a, I will reach state B. Okay, in state B, whenever I encounter either an A or a B, I will reach back to B. Okay, here from A, when I encounter a small b, I will reach C. And here, C, state C, when I encounter a small a or b, I will reach back C. You need not worry about how this diagram is drawn. We will be dealing with that later. First, let's see how the automaton works. Now, you know very well over here that the initial state is A. How did you know that the initial state is A? You knew that the initial state was A because A is the only thing which has just an incoming arrow, like, from nothing. Okay, so which means I am starting with my state A. So, whenever you need to check validity of a string, write the string on top first. Okay, write the string on top first. And then below, you are going to travel. You are going to traverse. Okay, so it's very simple. You can start only from A because A is my initial state. And you have to check on encountering A, where will you reach? To check that, you will have to go to your diagram. So check in your diagram from A, from capital A, state A, when you encounter an input called small a, where do you reach? Okay, so I reach, as per my diagram, I will reach a state called B. Okay, now I've reached B. Now, state B, encountering a small b, which state do I go? Okay, look here, state B, encountering a small b, where do I go? Okay, so encountering a small b, I go again to my state B itself. I am going to my state B itself. Okay, so I write B. What is my next input now? My next input is again a B. So I'll have to check from state B, encountering a B, where will I go? From state B, encountering a B, where, just a minute. Okay. Encountering small b, where do you reach? You reach again at capital B, as per the diagram. Now, the next thing you have to encounter is you have to encounter A. So, capital B, I encounter an input state B. I again reach at a state called B. Now look here, there's nothing more to encounter. I've encountered everything. I've gone through everything, which means, I traversed the whole string. Now you have to check. By the time you finish traversing the whole string, have you reached at the final state? What is my final state over here? My final state over here is B. Now, starting from the initial state, if you reach at the final state, it means your string is acceptable. This is how you check validity of a string. Now, we'll just see one more example so that you're clear. Okay. Now, we'll go for the second one. Check whether BBAB is valid. Okay. Whatever is the case, you have to start from A, because, as per my state transition diagram, I have to start from A because A is my initial state. You cannot start from anywhere else. Okay. And so let's start doing it. From A, when you encounter B, where do you reach? You reach at a state called capital C. Okay. You're now in capital C. You're being told to encounter a B. Okay. So let's see, where do we reach? From C, you encounter a B, which means you will again reach at state C. You will again reach at state C. Okay. State C, you are told to encounter a. C, I am to encounter an A, which means, I will again reach in my state C. I am now in my state C. I'm told to encounter a B. B. Okay. Which means, I am again in my state called C. Okay. The string is over. The string is over. I am in my state called C. From my state transition diagram, I know that C is not in the final state. C is not in the final state. So whenever you start from your initial state and you do not reach the final state, very simple, you will be rejecting the string. So this is how an automaton works. You given an input string, you give an input string, you can give whichever strings you want. You give in an input string, you check through the automaton. This is my automaton. My automaton is defined by my diagram. Automatons are nothing but diagrammatical representations. I go through my state transition diagram, and then I should be able to tell whether I am able to accept it or reject it. If I start from my initial state and I reach my final state, I will accept the string, which means, this is valid. This is valid. If I start from my initial string and I do not reach at my final state, I will be rejecting my string. So this is how an automaton works. Let's see the various families of automata. Now, finite automata, it is broadly classified into two. Finite automata with output and finite automata without output. Finite automata with output is classified into two. You call them Moore machines and Mealy machines. Finite automata without output, you classify it into three: DFA, NFA, and epsilon NFA. DFA is deterministic finite automata. NFA is non-deterministic finite automata. And the third one is non-deterministic finite automata with epsilon. So we'll start with DFA, deterministic finite automata. Now, deterministic finite automata, this is how the structure would be. You will have input. It could be a long string. You could have lots of inputs. You will be giving it to the automata states, and then you will be getting an output, whether you can accept it or not. So these are the main 5 things which you would be having in a DFA, in a deterministic finite automata. Because there are 5 tuples. You say it is a quintuple. You say it is a quintuple. This is how the quintuple representation will look like. Okay, so there are 5 entities. The first one is Q, the second one is sigma, the third one is delta, then you have Q0, and then you have F. So this is how a finite automata machine is formally denoted mathematically. So we'll see each one by one. Q is nothing but the finite set of states. Sigma is your set of input symbols. Delta is your transition function. Q0 is your initial state. And F is the set of final states. Okay, we'll go through each one. Now look here. Q, you can have many states. Okay, Q, you can have many states. F also, you can have many states, which means, there can be more than one final state. There can be more than one final state. There can be more than one set of states. But, initial state, you will be having only one initial state. So this is the formal specification of an automaton. It is a quintuple. You'll have a quintuple consisting of all the states, the input symbols, the transition function, the initial state, and the set of final states. Now, let's see in detail about the definition of a DFA. This is very, very important. Now, as we did see earlier, DFA is nothing but a quintuple. It is a quintuple which will have 5 entities. So let's find out each and every entity for this particular automaton. So, I do have a predefined automaton over here. So let's write the DFA for this particular automaton. So as we saw earlier, Q is the set of all final states. Sorry, the set of states or the set of all the states. Now, if you look into this diagram, you do have 3 states, namely A, B, and C. So that is my Q, the finite set of states. You will never have infinite. You will have a finite set of states. Now, sigma is nothing but the set of input symbols. Okay, so look onto the parts over here. Which all are the input symbols you have? Okay, I just do have 2 input symbols, which means, sigma is A, B. Then we have something called delta or a transition function. Let that wait. We'll see that later. Q0 is nothing but my initial state or my start state. We call it the initial state or the start state. Now, the initial state or the start state, as per my automaton, it is A. Set of final states. In my particular automaton, I do have only one finite state, which is B. So hope all of you are clear with what is Q, what is sigma, what is Q0. Q0 is my initial state A, and then F is my final state. Now let's learn in detail about delta. delta or the transition function. Now, delta is nothing but the Cartesian product of Q and sigma. Okay, so I write Q cross sigma. I'll just copy sigma. Okay, so it is my Cartesian product of Q and sigma. So what is Q? Okay, what is Q? We've already written what is Q. So Q is nothing but Q is a set called A, B, C. Cross. What is your sigma? Sigma also we know it is A, B. So now what delta does is, delta is the transition function which helps you in doing a mapping between your states, all your states and your input symbols. Okay, so now let's find the Cartesian product and let's do a mapping. Okay, so let's write each and every element of this Q sigma A. So the first one will be, okay, so the first one will be A, A. The second one will be A, B. Okay, so I'm done with my A. Now I'll go start with business with my B, A, and then I have B, B. Hope you remember the Cartesian products mathematical preliminaries. And then we'll start with C. I have C, A, and then I have C, B. Okay, so this is my Cartesian product of Q cross sigma. Now you will be doing a mapping to all the states. Okay, so which are the states you have over here? You have 3 states. You have only 3 states. You have a state called A, you have a state called B, and then you have a state called C. Okay, so what I'll do is I'll just copy this and then I'll write it over here. Okay, so that when you write, you'll find it easier. Okay. So yeah, now take back your diagram. So you have this. Now you have to do a mapping. Okay, so let's see. From A, okay, take the first one, A. From A, on A, where do you reach? I will be reaching in a state called B. So, I'll just take a mapping and then I'll draw a line. Okay. From A, when I travel, I will be reaching A. I'll just make it a bit I'll even change the color. Okay, looks pretty. Okay, so on A, I will be reaching, sorry, not A, I will be reaching B. A on A, I will be reaching B. Okay, next is A on, my word isn't listening to me properly. Yeah, it's now reached to B. Now let me do a mapping of everything. Okay. Now next we'll have to see A on B. A on B, where do you reach? A on B, you will be reaching C. Okay, A on B, you will be reaching C. Okay. Next is B on A. B on A, where will you reach? B on A, you will be reaching B itself. B on A, you will be reaching B itself. Next is what? B on B, where will you reach? B on B also, you will be reaching back on B itself. Next is what? C on A. C on A, where will you reach? C on A, you will be reaching C on A, you will be reaching C. You will be reaching C. Next is what? C on B. C on B, where will you reach? C on B also, you will be reaching. So this is my transition function for my finite automata. See, be it finite automata, non-finite, when I say finite automata, I mean, be it deterministic finite automata, non-deterministic finite automata, or non-deterministic finite automata with epsilon, all these entities in your quintuple, they will be same, except for my transition function. My transition function is the only thing which will differ. Remaining everything will be the same, be it DFA, be it NFA, or be it NFA with epsilon. Your Q, sigma, Q0, and F, the definitions will be the same. Only the definitions of your transition function, it will differ. Okay, so now you'll be able to see that, for each and every transition, you will have a particular state. Okay, see, but look here, for this particular state, you do not have, because you don't have any incoming arrows to A. And that is the problem of this particular design of the finite automata. So this is how you define a DFA. So when I write my DFA, I will write it like this. My DFA is the set of ABC, okay, comma, the next set, okay, the set of ABC, comma, the next set, A, comma, B. Then, you write your whole transition function, A, comma, A. See, this whole thing you write, this whole thing you write, A, comma, A, you write all that, A, comma, A, comma, B, A, comma, C, and all that, comma, then you have your initial state, and then you have your final state. So this is how you mathematically denote a finite automata. It will be a quintuple of finite set of states, your input symbols, the transition function, the initial state, and the set of final states. So let's start designing DFAs. Let's start designing deterministic finite automata. So the first question we have is, construct a DFA that accepts the set of all strings over sigma equal to AB of length 2. Okay, so sigma is already given. Okay, sigma is already given. So I write sigma is equal to AB. And now they've given a small condition over here. All the strings which you construct, it should be of length 2. So, that is what I define my language to be. So I write it like this. My language consists of W, where W is a string. Hope you remember this notation. The length, where length of the string is 2. So this is what is my question. So my question is, I have a set of alphabets A, comma, B, and then I have to make a language where the strings can contain only A or B, and the length of the string should be equal to 2, exactly 2, not less than 2, not greater than 2, only 2. Now, this is the set of steps you need to follow while constructing a DFA. Okay, so the first step is try writing the strings in the language. Okay, all times it is not possible. Try if you can write the strings in the language. Okay, so anyway, I do have an easy question over here which tells me only A and B, and length should be 2. So I know that I can have only 4 strings, AA, AB, BA, BB. So my first step is over. Okay, I tried writing it. I could write it. So this is my language. We'll go for the Next step, take the smallest string and construct a skeleton. Take the smallest string and construct a skeleton. So look here, all these are equal length. I'll go for the first one. I will take something called AA, and then I will try to construct a state transition diagram. Now, the state transition diagram, as we saw earlier, you have only 3 symbols for that. You have an arrow, then you have this particular thing for your states, and then if it is a final state, you have your 2 concentric rings to show that it is a final state. Okay, so let's try constructing the automata. Okay, so I will start with my initial state. You can give any name. Normally we start with A, B, C, D, E, F, G, and we go on. Or you can even write Q0, Q1. So whichever notation is easier for you, you can go for that. I am comfortable with A, B, C, D. So I will go with A, B, C, D. Okay. So I have an initial state called A. Now design a skeleton. First, let's simply go for a skeleton which can accept AA. Okay. So, I'll just draw a small skeleton over here. Okay, my initial state. Okay. I will be going to a next state. I will be going to a state called B. Okay. I'll just name this B. Okay. Now, look here. I am starting with A. Okay. So I will be writing A over here. Okay. So, I have now a string which I have now constructed a skeleton where from the initial state A, I am going to another state B, and I am encountering an input symbol called A. Now we'll have to even do one more because I have to encounter AA. So very simple. I go for my next state. I put B over here, not B. I'll just rename it. Let's say I am naming it C. And here I write A. Okay. So, I have done a skeleton for the state called AA. Okay, my initial state, I encounter an input symbol called A, I reach B, I encounter another input symbol B, and I reach the state called C, and that's it. Which means, you can say that this can be the final state. Okay, so what you can do is you can make it a concentric circle. Okay, you can make this a concentric circle telling that that is the final state. Okay, so you can make a pretty concentric circle. This is my final state. So I have satisfied things for AA. Now check all the possibilities by scanning the strings. Okay, so let's start. AB. Okay, so imagine you are to encounter AB. A. Okay, you don't have anything for B. Okay, you have only the next B. You have the next B, but you are encountering a next A over here. So you can give an A comma B. Drawing finite automaton is nothing but your imagination. It is the more imaginative you are, the better you will be able to draw finite automaton. So now I am able to satisfy both these. AA is over, AB is also over. Okay, so my finite automata is okay for AA and AB. Now the next string, what do I have? I do have BA. Okay, so very simple. I can write over here B comma A. Okay, small b comma A. So be it I encounter either B or A, I go to B, and then from B I encounter either A or B, I reach the final state C. Okay, now let's see if you can satisfy BB. Okay, you start from here, you reach B. Okay, you encounter small b, you reach the state called capital B, you encounter again a small b, you reach the final state called C, which means, this whole language I was able to satisfy. Okay, so for this particular language and this particular alphabet, this is my state transition diagram. Now, I have a step over here, check for a trap state. Okay, you will not encounter trap state over here. We will be encountering trap state in the next examples. We'll see that later. And we'll just complete it. And then I'll get back to your doubts. Construct a state transition table. Now, state transition table will look like this. Okay. Here, you will write your alphabets or your input symbols. I do have only 2 input symbols.
Excuse me, ma'am. Ma'am. Okay.
So here you will write your input symbols. I do have my input symbols over here, just small a, b. So I write it over there. And on this side, you will write all the states you have, A, B, C. And then you simply map. A on A, where do you go? You go to B. A on B, where do you go? You go to B. B on A, where do you go? You go to C. Okay, capital C. Okay, B on B, where do you go? You go to capital C. C is my final state. No, I don't go anywhere. I can't travel from there. So I simply give 2 dashes. So this is how you construct a DFA.